Okay, good evening everybody. Welcome to the last session of the day. I know it's been a long day and hopefully we're going to be glad to get it over with, get on to TechFest. And fortunately the topic of this last session is speed, making things faster. And if we can do it quickly enough, we'll get out of here, get our disco pants on and we'll be sorted. There will be no dancing in the session. All right, maybe a little bit of dancing. So what we're going to talk about today is the parallel extensions or parallel frameworks. They originally shipped with .NET 3.5 as the parallel extensions. They're now incorporated into .NET 4 as the parallel frameworks. And it's basically a helper library that assists with parallelism. And first of all, we're going to have a quick chat about why are we interested in parallelism, and in particular, why now? Why are we talking about it now? We're then going to look at the three components of the parallel extensions, which are parallel link. We'll spend most of our time on that, the task parallel library, and the underlying coordination data structures. So, since this is a talk that essentially it's about performance, it's about making use of the CPU, I'm required under New Zealand law to display a slide about Moore's law. But you guys all know this by heart. What's important, though, is that the impact of Moore's law has begun to change. If you remember the period from like when the PC was introduced, sort of the early 1980s, through to maybe 2003, 2004, chips were getting faster and faster and faster. Every time you turned around, they added another gigahertz or something ridiculous to the speed of the chip. That stopped, that hit a wall. The chips that we're seeing now, if you just look at the raw clock speed, then the numbers we're seeing now are pretty similar to the numbers that we're seeing several years ago. What's changing is that now we're getting multiple cores in those chips. This is, I think, about a 3-year-old laptop, and it's a dual-core machine. I bought a mid to low range, my old PC was dying, so I replaced it a couple of weeks ago with a sort of mid-range Dell machine, pretty commodity machine. That's a 4-core machine. But that means that if we want to take advantage, if we want our programs to take advantage of all those extra transistors, of all that extra capability, we can't just rely on our programs getting faster because the chips are getting faster. We've got to learn how to make use of those additional cores. And this is the kind of thing we're going to be seeing in I asked for that as my demo machine. That's only 128 cores. It will take like 10 years to get to that. But we'll get there. And seriously, that I believe is from an actual current shipping machine. You can get that many cores on a machine. And if you want to do really complex calculations, things like image analysis, video analysis, video processing, scientific computation, financial computation perhaps, large amount of statistical computation, then you need to be thinking about how you can use those multiple cores. You can't afford to have cores lying idle. And the good news is that with the .NET Framework 4, that capability is being brought into the core framework so as to make it easy for you to actually implement parallel algorithms, parallel programs that will take advantage of those multiple cores, that will gain the speed up that those multiple cores can provide. And this diagram just briefly shows the components of that. So you can see there's the unmanaged model, which you can see in orange, which you'd use from C++, and then the managed model, which we're going to be looking at today, parallel link sitting over task parallel library. That in turn is sitting over the traditional thread pool that we've had in .NET since the beginning, and those in turn sit over the Windows operating system threads and also user mode scheduled threads. Another thing that's been introduced in recent versions of Visual Studio in 2010 has been some additional tooling around parallelism, particularly around debugging parallel scenarios. And there's the picture. So, parallel link. It's like link, but it's faster. We'll talk about that later. Here's the problem. So I broke into the marketplace last night and stole some code from the Intergen booth. I don't know if any of you have been on that race car. I'm told it's terrifically exciting. You should go down there. But now, suppose you want to analyse the outcomes of those races. Now, fortunately, there's only about 2,000 people here. So if we do this for each loop, going over, checking, does it match the name? Have we got that many wins? Yada yada yada, and sorting the results. That's gonna work okay. I mean, on a modern processor, 2 or 3 gigahertz, that's gonna run pretty quickly. Now imagine the entire population of France visits the Intergen booth. Imagine it. 60 million Frenchmen all clustered around the Intergen booth. It's going to be fantastic. We're not going to be able to process a data set of that size efficiently just by iterating serially over those results. It's going to take far too long. Fortunately, being smart programmers who know our way around the .NET framework, we know thread pool. We can solve this. All we need to do is write a few additional lines of code that spin up some worker threads and allocate some work to them. We do the processing on those worker threads, and then we kind of put it back together again at the end. And I think, you can look at this, and I think it's pretty clear what's going on. No, you meant to laugh louder than that. What's the problem? What are the many problems with this? Well, firstly, let's look at the business logic. There's our original code in the context of all of this. So what does this tell you? Well, the business logic is, firstly, it's terribly intermingled with the logic of coordinating and managing all those threads. And it's also swamped by the logic of coordinating and managing all those threads. We've got all this detail about the physical issues of running on multiple cores, and our business logic is just being lost in all that. There's a few details that are particularly offensive. There we need to partition up the work. We need to figure out the number of partitions, try to judge what's going to be an appropriate number of threads effectively to run, number of tasks to create. Whenever I see get enumerator being called explicitly, that's usually a warning sign, but in this case I can't use a for each loop because each thread is going to have to pick off items, and you only want each item to be picked off by one thread. We can't have each thread running a for each loop, but we can't have the main thread running a for each loop either. So we have to do that get enumerator, and that becomes a shared bit of state. There's a lovely Win32 synchronization primitive lurking around, so now I've got to worry about manually stopping and starting my threads and coordinating them. That's just great. We have to lock the enumerator, so if we allowed all of those threads to access that enumerator without any locking, they could access it at the same time, then you might get thread A would call move next, then while it was going on to its next statement, thread B would call move next, then thread A would call current, then thread B would call current, and the upshot of that is that threads A and B end up processing the same item, and the one before it doesn't get processed at all. So we need to lock the enumerator, and that's going to cause contention. And then we need to use this interlocked construct and pass around refs to integers and generally track things and deal with manual reset events to set things back. And I think this can be summarized pretty effectively in one word. The most epic part of the fail, though, is not, I think, the code itself. The code is correct. It will work. I hope it's correct and will work. But in order to write it, the developer who wrote this has had to become an expert on concurrency. And our lords and masters do not pay us to be experts on concurrency, for the most part. They pay us to be experts in a business domain, to actually deliver business value, to solve business problems. And not only have I had to become an expert on concurrency in order to write this routine at the expense of working on business value, everyone who maintains this piece of code is also going to have to be an expert on concurrency. Every single maintenance programmer who touches this is going to have to get lucky. And I don't want to bet the company on that. This is so error-prone, it's alarming. Now, some of you may obviously have looked at that original for each loop and said, for each? Are you living in the 1.1 era? Why don't you use link? And of course, you're right, I should be using link. I can rewrite that for each loop as a simple link query with a where clause and an order by. And it turns out that if I do it this way, it actually makes it a lot easier to parallelize. So I need to watch very carefully here. And if you do that, that will now run in parallel using an appropriate number of cores. So, right, 11 minutes. Thank you very much for coming along. I hope it's been useful. No, you don't get away that easily. Let's do some demos. So the first demo I'm going to show you, all the demos, by the way, these are all written by the Parallel Extensions team. If you look at that URL down there, code.msdn.microsoft.com, the Parallel Extension samples on there, all of the demos I'm going to show you today are in that pack. So you can just download them, have a bit of a play with them. I guess another caveat I need to mention is that this is a reasonably old laptop, so it's not got very many cores, it's only got 2 cores. I so wish Microsoft had given me like an 8-core laptop to do really compelling demos on, but somehow it just never kind of happened. Still, we'll do our best. So let's kick off with the baby name sample. So this is a pretty simple kind of query. Let's just take a look at the query here. So if I'll run up the application, let's just run that up, and you'll see the kind of thing it does. So this is generating, firstly, it thinks for a while generating a synthetic data set, and initially it kicks off with, it just generates 3 million random records. And the records that it generates, the idea is they represent births by year and by US state. And it's just generating some random data. Now we're going to try to analyze those 3 million records. So here's the query that we're using. We're going to show the number of babies with a given name in a given state for each year. So we do a query on babies where name equals whatever, where state equals whatever, within a certain range, and we'll order it by year. So let's run that as a link query. You've just seen the query that's running now. Taking a little bit of time. It's chunking through those 3 million records. 5 seconds. Let's see if we can see that in action in Task Manager. So see how that's peaking around 50%? There's half of my computer is lying idle. Okay, let's have a look at what the other button does. And that runs a query that looks spookily similar. Babies, name equals, state equals, year is in range, order by. Just this as parallel. There's also this little wart, this with degrees of parallelism. That's just to support a little option for people who've got enough cores that they can actually use less than the full number. Curse you! Envy's a terrible thing. So let's have a look at how parallel link holds up. Same query, just with .as parallel. Wow, 1.8 times. That's pretty good. You're never going to quite get to 2 times on a 2-core machine or 4 times on a 4-core machine or whatever. There's always some overhead with synchronization, with merging, with rendezvous. But just by putting those extra few characters onto the query, we've nearly doubled the speed. I think if we do it again, we might get a slightly bigger speed up. Slightly, not really significant. And that is the only difference between those 2 queries, is that as parallel. You can even use this in, and this is just a straight .NET thing, we can even use this in an office environment. So if we bring up this is an example of Monte Carlo simulation in Excel. So here I've got a bunch of options, and sitting behind that, you can see if I've got run sequential, it's going to do this from cell in cells, select yada yada yada, does the let. That's where a lot of the work happens in that price agent options. So if I run that Monte Carlo simulation, you can see junk, junk, junk. It's going, but it's not going terrifically fast. So if I cancel that, I'm going to get an exception because the guy who wrote this decided he liked exceptions. There we go. Oh, no, I didn't mean to stop that. No, don't die. This would be a really great time to show you the parallel debugging windows. See there? Fantastic. Terminate the process. Yeah, that sounds good. Okay, sorry about that. Right, let's bring that up again. And let's just, once again, get a little bit of a feel for the how fast it is running non-parallel, running sequential. There's our exception. And we just want to carry on rather than stop the process. Now I'm going to change this so that it will run in parallel. And that's just triggering it to use to go down. Dunk, dunk. This code path instead of that code path. So it's the same thing, it's that from cell in cells, price agent options. So now we've once again got that as parallel. We've also got a few knobs on it which allow, for example, for cancellation and something to do with buffering and merging, which we'll talk about a little bit later on. So I've changed that to yes, and now I'll run that again, and you'll see it's going to fill up those same first few cells. Once it gets out of there, chunk, 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 you can see that's perceptibly faster to the eye. And if I was running on more cores, it would be faster still. There is an execution time down there which we could look at if we really wanted to get a figure for how much faster it was. But I think there's enough of a visual speed up that you can see that's made a real difference just by adding that dot as parallel. Okay, so what's actually going on here? I mean, I've told you everything you need to do, so if you want to get to TechFest, you can go now. But let's have a look behind the scenes. Let's try and understand what's actually happening here. So Parallel Link will make use of that additional hardware, those additional cores, for running link queries. But as you've seen, it abstracts away pretty much all the details of parallelism. But it doesn't abstract them away in a dumb way. It's not stupid. It's not naive. It actually partitions and merges data in quite intelligent ways. It actually analyzes your query and figures out what are good strategies for parallelizing this. And we'll talk about that a little bit in a few moments. It supports all of the .NET standard query operators, all of the Link standard query operators. And it's got a few additional knobs that you can tweak, a few additional operators, like we've already seen that with degrees of parallelism knob that you can tweak. And it works for any enumerable of T. You don't need to have a special parallelizable data source to make this work. Any sequence will do. Anything that can produce values, Parallel Link can cope with them, just as Link can cope with them. It has got some optimizations and special handling for other types, in particular iList of T, which also includes arrays of T, allow it to do some optimization under certain circumstances. And it also supports some customization of the way things are partitioned. So if you've got an algorithm or a data source that you know can be parallelized in a more efficient way than Parallel Link's default one, then you can tell Parallel Link how to do that. Parallel Link is built on top of the task parallel library and coordination data structures, which we'll talk about briefly at the end. So, writing a p-link query. Well, the natural way to do it is use that link syntax like we saw earlier, but put .as parallel on your data source. And that's it. You can also do it using the extension methods, and that as parallel, if you go and look at the definition of as parallel, you'll find it returns a parallel query of T. And there's a whole bunch of extension methods defined on parallel query of T, and you can use those explicitly. In fact, sometimes when the link syntax doesn't handle them, you have to. So you can, for example, put .where, and you'll get the parallelized version of .where rather than the serial version of .where, as long as it's running against a parallel query. Finally, all those extension methods are actually defined on a static class called parallel enumerable, so you could call those explicitly in theory. It's a pretty bad idea because it makes your code completely unreadable, but I mean, I know some of you hate maintenance programmers, so if you really want to. These are all the same. The compiler just translates the first one into the second and then translates the second one into the third. I've got a session tomorrow morning which will talk about the link compilation process in more detail, but this is just standard link. So all of those are equivalent, and just as in normal link, it's that bottom level API implementation, it's that static class, parallel enumerable, that's actually doing the work. Let's talk about how it does the pushing and merging, because that's really the key to Parallel Link, is the strategies that it uses it for actually parallelizing the queries. So what is partitioning? Well, the idea is that the input to an operator, so we've got a data source, we've got a sequence, we've got to partition that up into a certain number of disjoint subsets. So the number of degrees of parallelism, we're going to get a number of tasks, effectively a number of threads, equal to that number of degrees of parallelism. And we need to partition the data in such a way that each thread can do its work. So that means that each item has got to go into exactly one task, no more than one, and also no less than one. We don't want to skip any items. So P disjoint subsets. And then we need to replicate the operators across those partitions. So for each sort of partitioned sequence, task 1, task 2, task 3, task 4, however many we've got, we need to replicate those operators, the where operator, the select operator, the sum operator, across those partitions so that they can run on those partitioned subsequences. And those partitions can then execute in almost complete isolation. Sometimes there will have to be a little bit of a rendezvous. For example, in some cases, they'll have to share a numerator. There may be merging, buffering issues to consider. But basically, the actual execution is in complete isolation. One subtlety here is something that the parallel frameworks guys call operator fusion. Now, the naive approach to this would be, I'll get my subsequence, I'll apply the first operator to that, and I'll get the results out of all of that stuff. And then I'll move on and I'll partition it again, partition those merged results, pass them on to the second operator. Merge those results back, pass them on to the third one. So here we're doing you can see it's being split so that we can run a parallel where. The results of the where are being merged. They're being split so we can run a parallel select. The results of that are being merged. The results of that are being split again so that we can run a parallel sum, and eventually all that is brought back together. That obviously creates a huge bottleneck because you're doing a lot of synchronization, a lot of partitioning and merging. Everybody has to wait for the last thread to do anything. And then we keep having to do locks, we keep having to do synchronization. So P-Link avoids that trap. What it does is what they call it fusing operators together. So they partition once, and then they apply the where, select, and sum to each partition as a group. There's no need for a rendezvous in the middle. So it's minimizing the number of partitioning and merging steps, and it therefore runs pretty efficiently. What about the partitioning scheme itself? How do we partition this stuff? How do we decide how to divide these things up? Parallel has got a number of algorithms built in. It's got 4 built-in partitioning schemes, and we'll just run through those. The default one, the simplest one that works with any IEnumerable T, is called chunk partitioning. And this is pretty similar to what we saw in that horrible thread pool code, that basically we've got a shared enumerator. So the P-Link creates an enumerator, and then each thread, each task, goes and pulls data from that enumerator. And when it's finished working on one piece of data, it goes back to the enumerator and says, please, sir, can I have another, until the enumerator runs out. Now, this would be terribly, terribly inefficient, because if you had to go back to the enumerator for every single piece of work, you potentially have a lot of locking. If you were doing small work items, you'd have a lot of locking on the enumerator. The threads would be all trying to hit it at the same time. You've got like the Three Stooges trying to get through a door. It would just not work very well. So how do we solve that? Well, the obvious naive solution is to say, well, we'll hand out 50 work items at a time. So you don't have to rendezvous, you don't have to go and lock that thing so often. Unfortunately, that doesn't work so well either. If I've got a piece of parallel processing, say a ray tracer, which is going to be rendering 50 lines, each of which is one work item, but each of those lines takes quite a bit of time, then my first thread would go, right, I'll take the first 50, and then threads 2, 3, and 4 will go, what? Where? Where'd the work go? Meanwhile, core 1 is chugging away 100% locked on, and cores 2, 3, and 4 are doing nothing. So how does P-Link solve that? If you imagine each of those colours, unfortunately, I hope you can tell the orange and yellow apart, it uses a sort of an adaptive incremental approach. So the first time a task needs to rendezvous with the enumerator, needs to get a piece of work, it takes one piece of work. And it goes away and it works on that for a bit, and when it's finished, it comes back. If there's work to be done, it takes 2 pieces of work. And it goes and does those, comes back, takes 4 pieces of work, and so on and so forth. The exact details of how it adapts are obviously internal, but that gives you some sort of idea. So this results in a pretty efficient allocation of work. It ensures that each of the threads manages to keep pretty busy. The issue is that that single enumerator is shared, it is still locked, and that can cause inefficiencies. So for iList of T, if the data source implements iList of T, Parallel Link will use an optimization called range partitioning. And the idea is iList of T supports random access. So P-Link can just divide everything up right at the beginning. and go, right, task one, you can do the first quarter. You guys, you do the second quarter. You do the third quarter. You do the fourth quarter. And these guys, these tasks can then party on their subsets of the list. They've got a numeric range. They can just jump in to their bits of the list as and when they want to. They don't need to synchronize with things reading from other bits of the list because there's no shared enumerator. I'll show you an example of this in action. And again, this is coming from the parallel extension samples. And some of you may have seen the infamous LINQ ray tracer. This is a ray tracer written in LINQ by a guy called Luke Hoban, who is clearly insane. He's actually written an entire ray tracer as a LINQ query. And it starts here, and it goes on, 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 and it... There! Whoa! Yeah, finished. In the words of the Unix kernel, you are not expected to understand this. But it does actually work. So let's take a look at that. We'll just initially... come along. There we go. So if we run that up, we'll firstly just run it as a standard LINQ query. So this is using LINQ to objects. It's going to run on one core, and it takes about 6 seconds to do its work. Now, if I turn on that parallel button, then it's going to use the other. It's going to parallelize that query. So you can see this is the same query. I won't go through it all again because you obviously understand it now. But he's starting that list of rows. He's emitting them at as parallel. So now, when I turn that on, you can see the render is a lot faster. That's about 3 seconds now, just under 4 seconds. Now I want you to watch how that render happens. I want you to watch carefully, and particularly watch as we get towards the bottom of the screen. What you're going to see are some little black bands, and they're going to get a little bit wider. Do you see how they're getting a bit wider as you get towards the bottom? So initially they're starting out quite thin. Each thread is only pulling out a small amount of work, but towards the end they're pulling out more and more. So thread 1 and thread 2 are kind of going like that, and that's where that black band comes in. Stuff that thread 1 hasn't got to yet, but it's reserved, but it hasn't got to yet. Does that make sense? Can you see what's going on there? Yeah, cool, excellent. So let's make a change to show how range partitioning works. Again, very simple change. I'm just going to make it so that as parallel is running over an I list rather than a plain old I enumerable. So now, again, I want you to watch the black bands. Look at the difference there. You can see the range partitioning in action. Task 1, we've only got 2 tasks. Task 1 got given the top half of the range. Task 2 got given the bottom half of the range. And so you saw rendering begin at the halfway mark even before anything had come close to it. This also, by the way, illustrates one of the little dangers of range partitioning. In this case, there's a lot less work to do in the top half of the picture. Because there are no reflections to be calculated in the top half, task 1 was able to race down to about a quarter of the way before actually starting having to do any work. So we actually ended up with a situation where task 1, core 1, was sitting idle while task 2 still had work to do. And unfortunately, P-Link is not smart enough to actually analyze your 3D scenes and solve that one for you. The other 2 built-ins are a little bit specialized. The third one is something they call stripe partitioning. And this is motivated by the example of the LINQ take while operator. Now, if you think about what take while does, is it keeps going down sequence. It selects from the sequence as long as a certain condition is true. But as soon as that condition becomes false, it stops pulling things from the sequence and returns no more. So if you imagine a take while over a list using range partitioning, and imagine that the condition became false, say at the end of the red band there, then what you find is that task 1 would charge on down the red band. Everything would be, the condition would be true, so the take while will keep returning. Meanwhile, task 2, 3, and 4 will be charging down the orange, yellow, and green bands, blissfully unaware that in about 20 seconds' time, task 1 was about to say, hey, you guys, we don't need that stuff. I've got a fail case here. So when P-Link sees a take while operator, it uses this round-robin stripe partitioning. Task 1 gets 0, 4, 8, 12, and so on. Task 2 gets 1, 5, 9, 13, and so on. So again, it's random access, so there's no locking, there's no contention. But it means that in that take while scenario, you'll get less wasted effort because the other threads hopefully won't have gone too far down the road, too far past the fail point. There's potentially still some wasted effort, but it shouldn't be too much. And the final one that P-Link uses is hash partitioning. And this is, again, a little bit of a specialized one. It assigns elements to a partition based on their hash code. Why would you want to do that? The answer is if a distinct operator is in play. So if P-Link sees the distinct operator in your query, it will use hash partitioning. Why do we need this for distinct? Well, if we partition distinct in the way that we described earlier, naively using something like range or chunk partitioning, then each of those partitions could contain duplicates. The idea of distinct is to deduplicate. Now, if we use, say, range partitioning, suppose we were looking, suppose the name Stephen appeared in multiple places in that input sequence. In fact, suppose it occurred, say, in the middle of the red band, middle of the orange band, middle of the yellow band, and the middle of the green band. Then, because each subset, each of those bands would deduplicate, the distinct operator would be partitioned, but when it came to merging, we'd need to re-deduplicate because we'd get a Stephen coming in from each of those sequences. And that means we'd have to run a serial distinct. We'd have to merge those sequences and run one distinct over them in one thread, in one task. So pretty much wasting our parallel capability by having to rerun that distinct thing at the end. So with hash partitioning, you guarantee that all of the Stephens go into the same partition. None of the Stephens go into the other partitions. Therefore, the distinct on the partition, the distinct on each partition is sufficient to guarantee uniqueness when they're merged. We don't now need to re-deduplicate because we're guaranteed that all duplicates were eliminated within their partitions. Does that make sense to people? Excellent. For 6 o'clock on a Tuesday evening, this is pretty good. You can do custom partitioning. There's a class called Partitioner of T. Again, you can find that in the TPL documentation. Not going to dive into that. Merging is the other end of the process. So we've talked about how we can split the work up between the threads, but eventually we've got to bring that stuff together again. We only want one query result. We want it all in one place. How do we do that? Well, that's what merging does. And there are 3 merging strategies that P-Link will use. And again, these are based on how the thing is consumed, based on the operators that are used. The default, typically what you'll be doing is for eaching over the result, using the for each operator, the for each keyword, which comes down to get enumerator. And this allows P-Link to use its pipelined model. The idea of pipelined is that basically each result becomes available as it's returned or as the task that's processing it makes it available. So you've got very low latency. You're able to pick things up very quickly, access the data as it's available. But there is some synchronization overhead because now you've potentially got thread 1 getting multiple bits of data thrown at it at the same time. But it's able to get that first piece of data really quickly. If, on the other hand, there's a to-list or to-array or an order-by operator involved, then we're going to have to wait for all of the results. We can't really sort them efficiently until we've got those results. And certainly if you're calling to-array or to-list, you're asking for all of the results in one big block. We can't do this as available thing. So in this case, P-Link will use this stop-and-go merging strategy. In this case, because we haven't got a thread pulling results off as they arrive, that thread can actually be reused to process work items. And the idea here is that as each thread finishes processing work items, they stick them into a common buffer, the list or the array or whatever, and when they're all available, then the main consumer thread can grab them and do whatever it wants to do with them, have its evil way with them. This minimises the amount of context switching you've got going on, but it does result in much higher latency because you've got to wait for the last thing to become available before you can actually touch the first thing, before controls return to you. It also results in much higher memory usage because you've actually got to buffer all of those things. You know, again, it's population of France. We've got to fit 60 million Frenchmen into our computer. It's going to be a tight squeeze. The final merging method is the no merging at all method, and this is specialised to an extension method called for all. And for all performs an operation on each result, on each thing, but it doesn't return a value. And that means that nothing's going to be consuming the return value. There is no return value to consume. So the data can be passed to for all as it emerges from each thread, but it just disappears. There's no need to put it into a common enumerator for thread 1 to get it out. There's no need to put it into a list for thread 1 to look at. There is no consumer. So you can only use this with for all, and you only use it for its side effects. And this is a bit anomalous for LINQ. LINQ is usually about avoiding side effects. It's about returning values. But if you use for all, then you're using side effects, save it to a file, save it to a database, print it to the console, something like that. That's where for all comes in. That's obviously very, very efficient because you've got no buffering issues, no locking issues, nothing, but it can only be used in that particular scenario. Now, conditions apply. There are a number of things which just pretty much prevent you from using parallelism or require you to design around them if these are conditions you might envisage. So, for example, parallelism, parallel link does not guarantee that things come out in the same order you put them in. You can obviously control the order in which things come out by using an order by operator to put them in a particular order. But if you're not doing any particular ordering, then you've got no guarantees of the order. So if order is important, if it's important they come out in the same order they came in, you cannot use parallelism. Exceptions cause a problem, again, because you've got these multiple threads each charging down theoretically in isolation from the other one. If one of them hits an exception, what's it going to do? Is it going to stop and just stop processing data while the other ones carry on? Well, clearly you don't want that because it would give you an incomplete result. So what parallel link does is it wraps up all the exceptions that it sees before it can stop the other threads. It wraps them up in an aggregate exception, which gets returned to the consumer thread, or well, it's thrown from the call site. But this is a pretty bad scenario. I mean, there's not really much you can do in the face of something like this. So really, you want to be pretty careful that you're writing your queries in such a way that they are going to return values rather than throwing exceptions. So either use something like a where, parallel where, to get rid of data that you don't want processed, or use a parallel select to return a default value in that case, whatever's appropriate to your particular business scenario. But try to avoid exceptions. They're just not good for parallelism. An obvious one, but one that bears mentioning, thread affinity. If you're dealing with objects that have got thread affinity, parallelizing them is going to be a complete disaster. So if I take the collection of Windows Forms controls and say, hey threads, party on this collection, then the first worker thread that touches a Windows Forms control will cause a huge explosion. You're not allowed to touch properties of Windows Forms control or WPF control from the wrong thread. Parallelism is always going to happen on the wrong thread. So you cannot use thread-affine objects in parallelism. A rather subtle one, but an absolutely crucial one, is don't use it with things that will get slower when you parallelize them. Who'd have thunk it? We said earlier that parallelism does incur an overhead. You've got to create these multiple threads. You've got to partition work out. You've got to handle synchronization. You've got to handle merging the results. You've got a huge amount of overhead in parallelism. So you've got to make sure the amount of work that you're doing is actually sufficient to justify that additional overhead. Typically, if you're doing a small number of items and you're doing quick operations on them, it's not going to be worth it. If you're doing a large number of items and quick operations on them, it might be worth it. I mean, here we've got this select x times 2. Chances are it's probably not going to be worth it, but if you've got a really large number of items, maybe. So test, profile, don't guess, try it out. And make sure you try it out on machines with different numbers of cores. Understand what your target machines might be like and use the appropriate number of degrees of parallelism. Again, the more degrees of parallelism, potentially the more overhead you've got. So profile, test. Finally, side effects and mutability can cause real problems. It takes a peculiar, twisted genius to write a link query that modifies itself as it goes along. But I think we've all met peculiar, twisted geniuses in the programming arena. I could save 3 cycles there. Shared state is the bane of parallel programming because you'll get race conditions. 2 things will be modifying something in different ways at different times, and it become inconsistent, or something else will get a partially consistent snapshot, or you'll lose values because you've got last one in wins, and so on and so forth. Most queries don't do this. Sensible queries don't do this. If you try really hard, you probably can. Please don't try really hard. Just write natural queries. Okay, we've seen the link ray tracer demo. I haven't got a penguin-related demo in here, but I do have some monkeys. And I think everybody loves monkeys. So this is an example of running a genetic algorithm. And these are obviously fairly processor-intensive. There's a lot of computation involved. And the idea here is basically going to have a genetic algorithm which creates random strings, breeds those strings, and attempts to hit a target of a piece of fine Shakespearean prose. So if I kick that off using just the 1 core, you'll see it's trundling along. We're getting, process locked around 50%. We're getting about 15 generations per second. And you can see to B star or Nolpo, it's more James Joyce than William Shakespeare. Yeah, that's a quote from Finnegan's Wake Man. So let's have our exception because we like exceptions. And let's try that in parallel. And again, watch that generations per second. You can see it's moving much more quickly. You can see visually. And you can see that generation per second has pretty much doubled. We've got a really good speed up here. It still reads like Dan Brown, but you can't have everything. You guys all like Dan Brown, don't you? No, I'm cruel. Again, we'll have a quick look at the source code. I think you can probably guess what's actually what's going to be going on here. And here we go. No, it's not there. To read my notes. That's a bit shameful. Create next generation. So create next generation. Again, you can see this using parallel enumerable.range, which is kind of the equivalent to enumerable.range.as parallel. It's actually slightly different implementation, but it kind of does the same thing. It returns a parallel query over that set of integers versus a serial one. And everything else in that query is the same. So we're able to get that double speed up just by using parallel enumerable instead of enumerable. So the question is, if you use parallel enumerable partway through the query, does the bit before that get executed sequentially? The answer is basically yes. So it will depend on what the extension methods resolve to. So if you've got a data source which is an IEnumerable and not a parallel query, and you do some wheres and selects on that, then those will be done serially. Once you change it to a parallel source by doing a .as parallel, then anything after that will be done in parallel. It will be done by plink. Parallel enumerable is something you probably wouldn't introduce in the middle of a query. I guess if you're trying to combine one data source with a sequence of integers, that's the only way I can think of it appearing in the middle of a query rather than as the original source of a query. I'm not sure what would happen if you tried to combine a serial data source with a parallel data source. I think that would probably get done serially, but I'd have to try it out and find out. Does that answer your question? Sweet. Okay, so we've looked at parallel link, and we've seen that it's pretty cool, but there's actually not an awful lot to it. All the work is actually being done under the surface by the task parallel library. TPL's got a number of constructs in it, and we don't really have time to go into all of them, so I'm just going to mention some of the key ones and point you in the right direction for the more advanced ones. The difficulty with link is that it's always about returning new values, it's about returning new sequences. But often we've got something we want to do imperatively, we've got a set of operations we want to do, and it's not about selecting something new, it's about doing some work on something. And obviously we have the for loop and the for each loop in C# or Visual Basic, but those are serial. So TPL introduces two new library constructs. These are not language keywords, they're just library functions, and they can be used from any language, which do a for loop or a for each loop in parallel. They'll just run the body of that loop, the lambda, in this case the delegate. They will use the same partitioning strategy. Well, they will partition that out onto multiple threads, and I believe they will try to use chunk partitioning for this. For I believe we'll use range partitioning. For each, we'll use chunk partitioning unless it can determine that you've got an iList involved. The details, again, they're implementation details. You probably don't want to rely on them too much. And these just work exactly the same as the loops, except that things get run on a pool of worker threads. The constructs will not return until all of those threads are completed, so you still have to wait for the rendezvous. You can reason about the holding routine synchronously. So again, we've got some demos here from the parallel extension samples. And let's start out with the Boids. So what is Boids? Boids is a Windows Presentation Foundation application which makes triangles fly around the screen, which is pretty cool. And up there you can see how long it's taking to render each frame. You can see that's a little bit on the slow side, but if I press a secret magic key, then it will parallelize, and you can see the time has gone down and the Boids are flying about much more smoothly. How's that actually working? So let's have a look in here, and we're looking for the step Boids method. And the way that step Boids works is it calls parallel.forEach with the algorithm for computing the next set of positions. The reason it actually always calls parallel.forEach is just that the keystroke talks between the degree of parallelism between one and a number of processors. Now, why are we using parallel.forEach here? Well, as I said earlier, this is a Windows Presentation Foundation application, and that means it's using the MVVM model that you may have heard Randall talking about on Monday. It's using data binding. So we can't select a new set of positions. We can't create a new collection of positions. We have to mutate the existing Boids so that the bindings to the position and velocity can update. So we've got to change the existing objects rather than creating new ones. And that's what this is doing. So, for example, it's changing Boid.position is changing the existing object. That's raising a property changed event. That's triggering the binding, and the UI is therefore updating. So this is that example of imperative work that we have to do rather than selection of new values. Does that distinction make sense to people? See what's going on there? Cool. Sorry, can you say again, please? That's an excellent question. The question is, doesn't that violate the thread affinity that you were talking about earlier? And the answer is no, it doesn't, because the Boids are CLR objects. Of course they're CLR objects. But they are plain old CLR objects rather than being controlled. So if I look at the Boid class, that's it's a model visual 3D. That's a data object. It's a model rather than being a control. So it hasn't got thread affinity. So I can actually modify from any thread. It will raise the property changed event, and then, maybe a dependency object, I'm not sure. It will raise the property changed event, and then the binding will update. And the WF data binding infrastructure will take care of marshalling the change on one thread to an update of the control on its affine thread. But you're right, I couldn't actually pass controls and operate on those controls within a parallel.forEach. That's absolutely correct, yeah. Anything else you want to add? No, we're running a little bit. Oh, no, we've probably got time for another demo. We like demos. How about the game of life? People know the game of life? People familiar with it? Right, okay. Trouble with these demos all kind of look pretty much the same in that you kind of, you run them up and you say, look at the frame rate. I'll put an as parallel in there. Look at the frame rate. It's just too easy to actually make for meaningful demos. It's an outrage. Let's have a look at the game of life. So here we go. Let's bring that up. So we'll start that up, and you can see some lifey things wiggling away as life tends to do. And down there at the bottom, you can see we've got a frame rate of 7 per second, and bring on the parallel, and they start wiggling frantically, and the frame rate goes up to 13 and a lot. So that's pretty good. Again, what's going on under the surface? No, don't do that. What's going on under the surface there? Game of life logic, where are we? Bring up the method. It's the move next method, and what he's doing here is creating an action. He's creating a delegate, and then he's doing a parallel.for over the size of the model, or if it's not, or he's doing a sequential for over the size of the model, passing in both cases the same delegate, the same body, the same action that's going to be taken. Okay. There is another ray tracer demo. Again, it kind of shows pretty much the same thing, so I'm not going to run through that because we're running a little bit short of time. It's all in the parallel extension samples. If you want to have a go, it's a bouncing ball, which is always a good. I love bouncing balls, so bring it down, have a look. It runs about 1 frame per second, so it's not exactly StarCraft. Another thing in the task parallel library, we've got constructs in the language for sequential execution. A, then B, then C. TPL gives us this parallel.invoke, which will run the various items in parallel rather than in serial. Underlying all of these things is the task object library. So task object, an asynchronous operation. There's another variant of that represents an asynchronous operation that returns a particular result. You've also got this from async method that allows you to take a pair of begin-end methods. So for example, if you think about a web request has got a begin get response and end get response, you can use that pair of methods, bundle them up into a task using the from async method. You can then manage that task as a unit of work rather than having to worry about the details of managing those two methods and coordinating those two methods. You can also control scheduling to some extent, so the task scheduler is an extensible infrastructure for that, and continuation should allow you to chain tasks together. As one task completes, it kicks off another one. And these are just a few examples of the task APIs, which, again, you can look up the documentation, so we're not going to go into the details of these. These are actually fairly low-level things, but you can see, for example, that from async method, how useful that might be. Final level, underlying all of that, coordination data structures, kind of the lowest level, the raw materials on which all of this stuff is built. And again, I'm just going to point you at the relevant names. I'm not going to talk about these in any detail. So there's 3 chunks of coordination data structures. The first one is thread-safe scalable collections, so concurrent collections that you can use from different threads, and they will continue to run efficiently even as you use them from different threads. They'll minimize the amount of locking and things they have to do. When they do have to lock, they'll lock very efficiently. There's a bunch of classes for task and data management. Things like lazy of T, thread local of T, the aggregate exception we talked about earlier, the partitioner classes that we talked about earlier, things like that. Cancellation token, our friend that causes lots of exceptions, that's a bonus. And the third bit is the synchronization types. Again, if you look at the system.threading namespace, you'll recognize manual reset event and semaphore. Those are familiar concepts. These are just sort of slightly lightweight versions, managed versions of these. They're just a little bit more lightweight. You've also got these spin lock and spin wait things. Everyone always says, don't spin lock, don't spin wait, because you're just hitting the processor all the time while you're spinning. But actually, spin locks and spin waits, if they're very short, are very efficient. They're much more efficient than actually using synchronization primitives and using things like reset events. So coordination data structures use these internally for that very efficient locking and contention management. It's all in the documentation. If you're interested in these lower level types, have a look around and you'll be able to find out about them. So, I know you're all keen to get to TechFest, and I know that in about half an hour all your memories of this talk will have been obliterated. So I'm going to ask you to try and remember just one thing, just those 12 vital characters as parallel. Put as parallel, oh my goodness, they're going already, as parallel. Put that onto your query. P-Link will look after it, will figure out the right number of tasks, the right number of threads to use. It will figure out a sensible, efficient strategy for partitioning your data. It will figure out how to put those results back together again. It will make a really good job of doing that, probably as good a job as you could do, and you won't need to worry about those internals. Everything is taken care of for you. 12 characters, an hour session. I think that's pretty efficient. Thank you very much for your time.